Hi. Cool. All right. So, welcome back, physicists. Checking this out. I'm going to keep these three up here. So, today we will eventually be starting this, but we'll probably wind up using a few of these guys in the video today, or in the homework from last night, I would assume. So, check it out. If you want to find the gravitational force between two 15-kilogram balls that are 35 meters apart, which of these do we use? Red, green, purple. Trying to find the attractive force of gravity between two masses. It's red, right? We have G, 6.67 times 10 to the negative 11. We have mass 1 is 15 and mass 2 is 15. And the distance between them was however many meters. On number 8, we are shooting for... Did they word this question a weird way? What fraction is this? Okay. The force that we're looking at, what did you guys get? Scientific notation, I assume. 1.2 times 10 to the negative 7? Negative 11? That's not what this says. Should we check it real quick? Let's look. Do you guys have it on your calculator still? Probably not if you did all the other ones. Let's try. We have two 15-kilogram masses, right? So let's just plug and chug. Okay, if I know the force of gravity, and for anybody who hasn't done it yet, you're in luck because we're doing it right meow. G is 6.67 times 10 to the negative 11. Somebody confirm. I just don't have it written in front of me. That seems right. What's mass 1? And what's mass 2? And we're dividing it by 35 what? Good. Okay, plug and chug. Check your calculators for me real quick. I'll do the same. I do get negative 11. I disagree with your book. Okay, verify for me real quick so we know if we need to go through this. 1.2 times 10 to the negative 11th. Newtons. And I gotta think this out. If anybody made a mistake, there's two places where there's really one place where I think it happens. I think it happens when you forget to put parentheses around that. That's like the most common spot. Cool. The second part, if you did it, awesome. It's asked to the ratio of the strength of this compared to the, what does it say, the mass? To the weight of one ball. I should have omitted that part. If anybody did it and you're feeling confident, I'm open to answers because the one that I have is very different. I have 8.4 times 10 to the 3 parts per billion, but that's just going to be, let's see, if we have 8.4 times 10 to the 3, that'd be this over this number. And let's see here. That's 10 to the negative 9, right? So, 8.4 times 10 to the negative 6 should work. That's ugly. I'm not going to ask you a question like that. That's a silly question. I don't like it. Is gravity very strong? No, that's the whole point. Like, it's almost nothing compared to the gravity of Earth that pulls down on the ball. All right, so we're not going to look at that one. Let's check it out. Number 9. Just going through. How long... What's the period of Neptune? How many years, Earth years specifically, or days, if you got that? Or seconds, if you got that? Not everybody at once. What'd you get on number 9? 164 what? 164 years. Thoughts, arguments, okay with that? I think that mine's giving me the wrong answers as I'm looking at it. Neptune, that seems reasonable. Not to spin, but to go 1 year on Neptune, to all the way around the sun. Because it's way out there, man. That's the last planet. Thoughts? Disagree? Agree? My book is clearly wrong. Mine says 6 days, but that's not true. Okay, here's the deal. I don't trust my answers that usually they're pretty good. For those of you that finished it, you're in luck. You don't have any more homework tonight. If you didn't finish it, it's going to be due for everybody tomorrow. Cool. Deal? Rather than checking them all, some of you have it, some of you don't. I will do them tonight because I don't trust my book answers here. Due tomorrow at the start of class. Cool, cool, cool. I will also do them so that I can get good answers. All right. So, if you're watching this at home, I'm going to take a trip away from the video for right now. And just so you can see it, here's what we're going to watch. And we're going to watch this briefly. I'm not going to record it because that makes the recordings huge. Remember, this is 5 levels. Before we watch this, I want you to spend a minute. We spoke about gravity a little bit, and we've looked at the mathematical relationships. I just want to ask a question. What is gravity? How does it work? Those things. Talk it out for a minute with your neighbors, and we'll see what you guys come up with. I'm not going to make everybody speak out loud, but I want you to try to explain gravity to each other. And then we'll watch at least the first 3 levels. So I'll give you like a minute or so. What is gravity? How does it work? What causes it? So forth, so on. Do you know more about gravity right now than you did a minute ago? Maybe. I hope so. But a lot of that, I listened to this the other day on the walk, and when I listened to the last one, bits and pieces of it would click in my head, but it was pretty far out there. So the good news is that we don't have to deal with it at that level because we're not PhD students yet. Okay, so for today, we're going to continue on. And again, I will give you tonight to finish the assignment from yesterday. But we're going to start today's stuff. I'm not going to give you any new homework, but we'll front load it now so tomorrow we can do a bunch of examples. Cool. So up on the board, I have a few different things, and I started trying to label this for you guys, but without building that image, it doesn't really mean anything to us yet. So I'm going to take that out for now. And what I have up here is 7.2. I'm going to start calling this n-lug instead of just nug for Newton's universal gravitation. We're going to call it Newton's law of universal gravitation. And we're jumping in here. These are the formulas from the first section that we dealt with. Now, as we get rolling, just a quick check. We should have them. What do these letters represent? TA over TB? Is what? Orbital period. Cool, I'm fine with that. So T is orbital period. I'm not going to label all of these because some of them I don't think necessarily need it. This is all the force of gravity. What's G? Capital G specifically. Before the number, I know the number roughly. Love it. Confidently whispered. Is gravitational constant. And that was discovered by Newton, right? So gravitational constant confirmed by Cavendish. Again, Friday, we'll get that experiment set up to run over the weekend and hopefully get some data. And we'll just make sure we have this. This is 6.67 times 10 to the negative 11. And that is Newton kilograms squared per meter squared. Cool, right? Newton kilograms squared per meter squared. That looks right to me. Okay, I think that's all we need. What's R? What sort of radius? The orbital radius. Now, realistically, I'm fine if we call it just the radius and the period, but as long as we're confident and remember that we're talking about the orbital stuff, then I'm fine with it. All right, so that's where we're jumping in. Now, we have all of this kind of background or prerequisite stuff that we're going to continue to use, and we're going to keep expanding on these ideas. So again, yesterday I gave you guys note cards. Hopefully you put these on there. We're going to add to them. at some point, and you should today. But to start looking at stuff, our first section for today is we're going to look at the orbits, and we're going to look primarily from Earth, but not always. But we'll start with orbits of planets, which we've already discussed a bit with Kepler and Newton, but more specifically, satellites. So how do planets and satellites act together? And I'm not going to define this right now, and I don't think we need to, but if I say a satellite, what do you guys think of? What do you think of, Nick, when I say the word satellite? Okay, so you might be thinking of Elon Musk and Starlink because there's a bunch of satellites that orbit our Earth for that purpose, right? Okay, now, anybody think of something that wasn't man-made when I said satellite? So asteroids are also satellites. They're not man-made. They're not like big spaceships or chunks of metal that we shoot up into space, but they are satellites. Anything that orbits, you can be considered a satellite. The moon is a satellite. Right off the bat, like it is a satellite of Earth. So, a couple things, again, not a history class. How many planets are there? Well, that's not the right answer. Toli, how many planets do you think there are? There are 8 of them. What's the first one?
Sun.
That's not a planet. That's a star, but I love it.
I was thinking of the...
You're good. So the sun is in the middle. Okay. What's the nearest planet? He's real fast.
Mars.
Mercury. Okay, so Mercury's really close, and then who? Let's see. Fern, who's next? Mercury? Venus, the hottest planet. Global warming gone crazy on Venus with all the greenhouse gases that exist. Third planet, Abigail. Earth. Fourth planet, Rafa. Mars. Fifth planet, anybody? Jupiter. Okay, 6. Wait, yeah, 6. Saturn. 7. Uranus. Okay, so check this out. Telescopes and things like that came out. They started being developed in like the 1500s with Galileo. The technology kept improving as time went, right? So that's naturally what happens. In 1781, Uranus was discovered. And within the next like 30 or 40 years, what they decided, based on observations of how Uranus travels around our sun, they said, wait a second, this doesn't follow Newton's laws. Now you have two choices once you realize that Uranus does not follow Newton's laws and Kepler's laws. Your first option is Newton and Kepler were wrong, and it's just total coincidence that every other observation that they've shown to be true works. That could happen. Gosh, or what else could cause it to be wrong other than Newton and Kepler being incorrect? We pull on the sun, right? Just like the sun pulls on us. We saw that gravity was a two-way street. Do we pull on Mars? Yeah, we must a little bit, right? Not a ton, but we pull on Mars and that impacts Mars' orbit. Do we pull on Jupiter and Saturn and Uranus? Less so, but definitely. I physically, just me, not even a planet, pull on the farthest element or the farthest atom in our entire universe because there's gravitational attraction between us. Now it's so small that no, it's not really attraction, but it's there, it exists, just almost zero. Okay, Uranus doesn't follow the rules, which means either they were wrong, they weren't, or there must be something else out there that's pulling on it. So, in 1780 is when Uranus was discovered. They tracked its movement, said, nope, it's wrong. There must be another planet out there. That's what the conclusion that they came to was. There's something that's messing it up. And it turns out, in 1845, they discovered Neptune. So they knew there was a planet before they could see it, which the mathematics and the physics tells us that. Now, as we go through this, Newton had already started to think about how orbits work, and they actually touched on it on the video that we just watched. So we're going to think about an orbital thought experiment. Now, when we're looking at thought experiments, this is a philosophical tool, orbit thought experiment, and all that it tells us is, well, let's just think about this and see if we can't logically come up with something without the math and so forth and so on. So this was a Newton idea, but here's what he was thinking, and he had a cannon. I'm going to get a nice circle up on my page. If you guys want to get a circle, I'll go to Desmos and grab one real quick. And let's see, x squared, plus y squared equals r. Whoa, equals, we'll just do 1. Okay, it's going to be a red circle, so we'll deal with it. Cool, beautiful, lovely circle here. Now, Newton imagined that on this circle, let's say it's the sun, for example, or, sorry, our Earth. That was a weird slip. Okay, here we have our Earth, or Mars. In this case, it's red. But he had this thought. He said, hey, I'm going to put a gigantic cannon, and I'm going to start blasting it. So I'm not going to draw a cannon. I'm going to draw a person that's like a giant. So Attack on Earth is now the show we're watching. Cool. He's going to throw stuff. And this is his thought experiment. Let's say first time he kind of noodle arms it, like just a little bit. If we have something projected, or a projectile, right, launched on our planet, and it leaves this giant's hand, what would the path look like? Is it just going to do this? Like if he throws it tangent to the Earth, so he's going to throw it this way, is it just going to go forever if he just kind of lightly throws it? Is it just going to go straight down like this if he lightly throws it? What's the path of it going to be? It's a curve. Now, specifically, it's a parabola, right? And what we just saw in the video is the curve that you're seeing is really and truly the curve of space itself, but that's not the main focus here. The first one, it's not going to be perfect, but do you guys agree maybe if he just kind of weak arms it, it does something like this? Okay, so Newton had this thought. He says, okay, well, that's fine and dandy. This guy could throw it harder. What if he throws it just a little bit harder? What would happen to the curve that this thing follows? If he throws it harder, is it going to land in the same spot? Where's it going to land? Farther. So, and I'm just making up how hard he throws it. If he throws it really hard, maybe a little bit harder rather, and this works really well on a small circle on my page, is it possible it lands over here now? Okay, so that's all fine and dandy. It's getting longer, further path it travels, right? Can we throw harder still? Now, obviously, we're not really giants doing this, but let's assume that this guy did. I want you guys to draw a little bit harder. Let's say, I can't tell you a number, but not hard enough that we wind up like circling the planet, but a little bit harder. Show me where you, like, show me a projected path of where something could land. A bit harder. Nice Toy. Nice Bea. Nice Fern. Nice Felicia. Nice Delilah. Nice. Love it. Okay, now I'm going to add 2 more on mine. What I see most of you guys doing, and here's where I'm going to start struggling, is it goes out. Is it possible that it hits like over here? Absolutely. We take advantage of this when we launch ballistic missiles. Hopefully we don't have to actually watch ballistic missiles get launched. But if we want to shoot a planet or shoot something to the other side of the planet, this is the path that it follows. Okay. If we go harder still, and I'm only going to draw 1 more, but eventually I can throw it so hard that the path that it follows is the same path and the same curve as the planet itself, right? And eventually if I throw this hard enough, it winds up bonking me right in the back of the head. By going faster and faster and faster as I throw, that curve starts to get less curved, and that's a weird way to word it, but if I'm saying less curved, here's really curved, here's less curved, less concavity, you might say, and eventually we can get around the planet. So this is Newton's big idea long before the realistic possibility of this happens. Again, his was a cannon. I can't draw a cannon. But here's what he realized. If we have a large enough, and I'm just going to call this VI for what? Initial velocity, we get orbit. Now, what we're going to do at the start of class tomorrow, because that's the end, what we're going to do at the start of class tomorrow is figure out how would we actually determine this velocity. So we're going to be jumping in right away tomorrow talking about the velocity of a satellite as it orbits our planet. Later, Raiders. Finish your homework tonight. Come talk to me if you have questions.